Okay, the last thing I showed you was the Walter Fent uh, spring pendulum demonstration. Now we're moving on to section 7.7, conservative and non-conservative forces. Imagine the book and the figure has been accelerated by your hand and is now sliding to the right on the surface of the table and slowing down due to the friction force. Now, suppose the surface is the system, the friction force from the sliding book does work on the surface. Uh, Now, positive work has been done on the surface. There's no increase in the surface's kinetic energy or potential energy of any system. Work has been done. Where is the energy? The surface will be warmer after the book slides over it, like sandpaper in the opening storyline, if you read the opening storyline. Work that was done on the surface has gone into warming the surface rather than increasing its speed or changing the configuration of a system. Energy associated with the temperature of a system is internal energy, symbolized by E subscript INT, internal energy. Here, the work done on the surface represents energy transferred into the system, but it appears in the system as internal energy rather than kinetic or potential energy. Now, consider the book and surface as a system. After the book is released, while slowing down, no work is done on this system. Initially, the system has kinetic energy because the book is moving. While the book is sliding, the internal energy of the system increases, and the book and the surface are warmer than before. When the book stops, the kinetic energy has been completely transformed into internal energy. Consider the friction force within the system, that is, between the book and the surface, as the transformation mechanism for energy. The force transforms kinetic energy of the system into internal energy. Uh, Rub your hands together very briskly, and you'll feel them warm up. As a matter of fact, on a cold day, that's what people do. They just take their hands and they rub them together to warm them. Now the figures on the right are the energy bars. The figure in B, the system contains kinetic energy at the instant the book is released by your hand, and it defines the reference amount of internal energy in the system as 0 at this instant. So it's all kinetic energy, 0 internal energy, and the total energy is all the kinetic energy. Now, in figure C, the kinetic energy is transforming into internal energy as the book slows down due to the friction force. So the velocity is decreasing, so 1/2 mv squared is decreasing. The internal energy is increasing. After the book has stopped sliding, the kinetic energy is equal to 0. We're looking at D now, and it's all internal energy. Um, so the system now is only the internal energy. The surface and the book is warmed up. Note the total energy bar in red doesn't change during this process. The amount of internal energy in the system after the book is stopped equals the amount of kinetic energy in the system at the initial instant. This is an example of conservation of energy, which we will explore in the next chapter. Conservative and non-conservative forces. Let's consider an object moving downward near Earth's surface. The work done by gravitational force on the object does not depend on whether it falls vertically or slides down the sloping incline with friction. The only change in the object's elevation is important. Only the change in the object's elevation is important. MGH, or mg delta H in this case. Energy transformation to internal energy due to friction on that incline depends on the distance the object slides. The longer the incline, the more potential energy is transformed to internal energy. The path makes no difference when we consider work done by gravitational force. It does make a difference when we consider energy transformation due to the friction forces. The forces are either conservative or not non-conservative. Gravitational force is conservative. Friction force is not conservative. Um, okay, conservative forces. Work done by a conservative force on a particle moving between any 2 points is independent of the path taken by the particle. Another factor in conservative forces is the work done by a conservative force on a particle moving through any closed path is 0. In other words, if it starts here, goes up and comes down, let's say it's gravitational force. If you took it up and brought it back down, the energy you put taking it up, gravity brought it back coming down, and the total energy, the work done is 0. Okay. Now, a closed path is one for which the beginning point and the end point are identical. So the examples of conservative forces are gravitational force, force that ideal spring exerts on any object attached to the spring, and the work done by the gravitational force on an object moving between any 2 points near the Earth's surface is shown. The work done is minus mg j because it's vertical, y final minus y initial j, so it's j dot j, so it's mg y final minus mg y initial, and wg depends only on the initial and final y coordinates of the object, and it's independent of the path. Whether it drops down like this or whether it goes down a track or down a ramp, the change in potential energy is only dependent on the y coordinate. Wg equals 0 when the object moves over any closed path. Okay. For the object in the spring system, the work of the spring is done by a spring force given by this. The work is equal to 1/2 kx initial squared minus 1/2 kx final squared. So the spring force is conservative. The work of the spring depends only on the initial and final x coordinates of the object and equals 0 for any closed path. Okay. So the force is non-conservative if it's not path independent, and it's non-conservative if the work for the closed path is not 0. Work done by a conservative path, work done by a conservative force is path dependent, and the sum of kinetic and potential energies of the system equals the mechanical energy of the system. So E mechanical is equal to the kinetic energy plus the potential energy. It includes kinetic energy of all moving members of the system, and potential U equals all types of potential energy in the system. For a book falling under the action of gravitational force, the mechanical energy of the book and the Earth's system remains fixed. Gravitational potential energy transforms to kinetic energy, and total energy of the system remains constant. Non-conservative forces acting within the system cause a change in the mechanical energy of the system. As an example, the books are sent sliding down on a horizontal surface that is not frictionless. The mechanical energy of the book surface system is transformed to internal energy. Only the part of the book's kinetic energy transformed to internal energy in the book. The rest appears as internal energy in the surface. Because the force of kinetic friction transforms mechanical energy of a system into internal energy, it is a non-conservative force. Now, suppose you displace a book between 2 points on the table, as in the figure. If the book is displaced in a straight line along the blue path between points A and B, you do a certain amount of work against kinetic friction force to keep the book moving at a constant speed. Now imagine pushing the book along the brown semicircular path. You perform more work against friction along the curved path because the path is longer. Work done on the book depends on the path, so the friction force cannot be conservative. Okay, this ends the section on conservative and non-conservative forces. Next, we will discuss section 7.8, relationship between conservative forces and potential energy.